Okay, welcome to the fourth installment in the short video series, Molar Mass. And what we're going to do today is actually go full circle back to the very first video where we started all this business. And what I want to focus on in this video is how to calculate the molar mass of a compound or a molecule. Because previous to this, we focused on mass mole atom calculations that involve singular elements. So now what we're going to do is elevate the sophistication of this to situations where we're dealing with molecules and compounds. So what I'm showing here on the diagram is the reaction between iron ore and carbon to produce iron metal and carbon monoxide. So iron ore, the carbon, to produce iron metal, carbon monoxide. Now I want to draw your attention to these numbers, to the numbers that precede each of the components that are in the chemical equation. So for the iron ore, there's a 1 that precedes the compound. For carbon, there's a 4. For iron metal, a 3. And for carbon monoxide, 4. These numbers are called coefficients, and they provide information about the relative proportions in which the various components of a chemical equation are required to react. And they have units of moles. So remember, a mole is like analogous to a dozen, where a dozen is equal to 12. Very simple number. In the case of the mole, though, a mole is equal to 6 times 10 to the 23rd of whatever, of particles, molecules, atoms, apples, oranges, whatever the situation. A mole, though, is equal to 6 times 10 to the 23rd. Versus a dozen, which is equal to 12. So what this equation is telling us is that it requires 1 mole of iron ore to react with 4 moles of carbon. So the goal of this video, well, actually there's 2 goals of this video. The first goal is to learn how to calculate molar masses of molecules, but the second goal is to calculate how much mass of iron ore we need to react with 4 carbons. So as we get started with this, what I'm going to point out first is that we already have determined the amount of carbon we need. We know that 1 mole of carbon is 12 grams. And in the first video, I demonstrated that on a scale. I showed how you could mass out 12 grams of carbon, and that was exactly 1 mole. Since we need 4 moles of carbon to react with every mole of iron ore, then it's going to take 48 grams of carbon to run this reaction if it's run exactly how it's illustrated by the balanced equation. So we want to know how much iron ore in terms of mass is required to react with 48 grams of carbon. That's another goal of this video. Now, before we can answer that question, what we need to do is talk about what a chemical formula means, because again, to emphasize the fact that we're not dealing here with a single element. Iron ore is composed of 2 elements. So what is a chemical formula, all right? A chemical formula is a simple notation that involves 2 factors. One of those factors are atomic symbols. So the chemical formula is going to include the atomic symbols of all the elements that appear within that compound. So in the case of iron ore, there's iron and there's oxygen. The second thing a chemical formula will include will be a number that appears as a subscript down and right of a particular element that gives us the relative proportions in which that element appears within the compound. So for example, the iron ore is Fe3O4. And what does this mean in reality? It means that in iron ore there are 3 atoms of iron and 4 atoms of oxygen. Another example is H2O, water. In the formula, we see that the subscript 2 follows down and right of the hydrogen. So that means that there are 2 hydrogens in every molecule of water, and there is 1 oxygen. Sodium carbonate. In this compound, there are 2 atoms of sodium, 1 atom of carbon, and 3 atoms of oxygen. Ammonia, 1 atom of nitrogen, and 3 atoms of hydrogen. So understanding how to read a chemical formula is super important in chemistry. So 2 pieces of information in a formula: the atomic symbols that tell us which elements have been combined through chemical bonds to produce that compound, and secondly, the use of subscripts that follow down and right of a particular element that tell us the relative proportion in which that element appears within the formula. Now, how do we calculate the molar mass of a compound? In the case of an element, it's simple. All you have to do is look the molar mass up on the periodic table. So for example, if we want to know the molar mass of carbon, all we have to do is look it up on the table. It's 12. If we want to know oxygen, we just look it up. It's 15.9, or rounding, it's 16. In the case of fluorine, 18.9, or we could just call it 19 for the sake of this video. So a periodic table is needed in order to identify the molar mass of an element. It's just a little trickier with the compound, but not much. So in the case of a compound, what we have to do is look up the atomic masses for each of the atoms that appear in the compound, and we have to compensate that molar mass for the number of times that element appears in the formula. So in this line here, what I'm showing is that statement. So there are 3 irons plus 4 oxygens. So what we're going to do is look up the atomic mass of each element that appears in the formula, and then we're going to add that together, accounting for the number of times a particular element appears within the chemical formula. So for iron, we look up the element on the periodic table, and the molar mass is 55.8. For oxygen, it's 16. There's 3 irons, and there's 4 oxygens. So we multiply the 3 times 55.8 and the 4 times the 16, and then we sum the whole thing together for a mass of 231.4 grams per mole. So calculating the molar mass of a formula or of a chemical compound is simple. All you need to remember is that you need to look up the molar mass of each symbol that is in the formula, and then add the molar masses together, accounting for the number of times each element appears within the formula. So going back to the start of the video, what we're going to do now is solve one of the 2 challenges. And the challenge that we're going to solve is to determine the mass of iron ore required to react with 48 grams of carbon. Since the equation tells us that 1 mole of iron ore must react with 4 moles of carbon, then it will take 231.4 grams of iron ore to react with each 48 grams of carbon. So we know the answer to the first question that we asked at the beginning of the video. Secondly, we can also know the iron. It takes 3 moles, or we're going to produce 3 moles of iron metal when the 48 grams of carbon reacts with the 231.4 grams of the iron ore. So to figure out how much metal we're going to produce, it's simply a matter of multiplying the coefficient for the iron times the molar mass, which is 55.8. So we're going to end up producing 167.4 grams of iron out of this reaction. By the same token, we're going to produce 112 grams of carbon monoxide. One of the interesting things here before we move on to practicing calculating molar masses is that if you add the mass of the carbon in this reaction to the mass of the iron ore that was utilized, and then you add the mass of the iron metal produced in the carbon monoxide, you will discover that these 2 masses, the sum of these masses, are equivalent, which has to be true because the law of conservation of mass tells us that mass has to be conserved in a chemical reaction. Now, in this last bit, what we're going to do is practice calculating some molar masses. So we're going to need a calculator, and we'll just go through this now. So for the first example, there are 2 sodiums, there's 1 carbon, and there are 3 oxygens. All right? The sodium has a molar mass of 23. The carbon is 12. And obviously I'm doing some rounding here to simplify the situation. And the oxygen is 16 for a total of 106. Make sure that this is the number that you're getting as you follow along. For ammonia, there is going to be 1 nitrogen, and there are 3 hydrogens, worth 1 each. So the total will be 17. For carbon dioxide, there's 1 carbon, worth 12, and there's 2 oxygens, worth 16. You should get a total of approximately 44. For potassium permanganate, the potassium is worth 39, and there's 1. The manganese, there's only 1 atom of it, and its molar mass is 54.9. And then there are 4 oxygens. All right, this one's a little trickier. So the oxygens are worth 16 each. So it's going to be 4 times 16. All right, plus 54.9 plus 39 equals approximately 158. Now this last one is an example I'm using because it represents essentially a scenario that students usually find a little bit more difficult. Because notice in the formula there is a parenthesis around another compound that's within the compound of the magnesium nitrate. So how do we figure this out? All right, we have a parenthesis around NO3, and outside the parentheses and down to the right is a 2. What this 2 means is that there are 2 NO3s within this bracket. So to figure out the molar mass of this compound, what we're going to do is calculate the molar mass for what's inside the bracket, and then we're going to multiply by 2. So there are 3 oxygens times 16 plus the molar mass of nitrogen, which is 14, for a grand total of 62. We multiply that number by 2 because the 2 means that there are 2 of these inside the bracket. So we're going to multiply 62 times 2 for a grand total of 124. And that is going to be added to the molar mass of magnesium, which is 24.3, for a total of 148.3. Okay, so hopefully you followed along and you've gotten numbers that are pretty close to what I have here.